1, 2, 3, Module 10, Part 2. So in Part 1, we introduced the logic circuits up until the discussion on the diode logic family. So for this part, we'll be looking at two other logic families. So that's the resistor transistor logic, or RTL, and the NMOS logic. So for resistor transistor logic, this is the type of logic wherein the diode switch is replaced with a BJT switch. The main issue with the diode logic is that it's difficult to cascade logic gates, because if you can remember, every time that in the logic gate the diode is turned on, there's always a 0.7 volt drop across the diode. So you can just imagine if you cascade logic gates and each logic gate has to turn a diode on, then dumadami yung mga 0.7 volt drop na yun, and there is a chance, actually a very high chance, that the logic at the output would be wrong. But so that's the good thing with resistor transistor logic, you can cascade it, but using BJTs actually translates to a large power draw. So that means the logic gate has a high power consumption. So to introduce RTL, we first look at the common emitter amplifier. So let's recall the voltage transfer characteristic of the common emitter amplifier shown here. So you will notice when we discussed, or you'll remember when we discussed the common emitter amplifier, we always emphasized the region of operation to be in this region here. No? It's a forward active because this is the region where you have gain. But if we actually look at the other regions of these voltage transfer characteristics, okay, if we look at the region where it is cut off, okay, the voltage input, the voltage levels at the inputs are low, but the output is high, 5 volts, right? And then if we look at the region when the BJT is in saturation, okay, so these would be, so you could actually extend this, no? So that would be our high voltages, high voltage, okay, so this is low input voltage. And on the right, we have the high input voltage. And the corresponding output would be 0.2 volts, or what we can interpret as a low output voltage, right? So the common emitter amplifier actually is our RTL inverter. But this time, okay, the way that we operate it as an inverter is by toggling the region of operation of the BJT into either cutoff or saturation. Okay, not in forward active. We don't operate in forward active. So kumbaga sa voltage transfer characteristic nitong RTL inverter, forbidden region. Okay, yung, or not forbidden, but indeterminate region, yung region kung saan nag-amplify siya. Okay? So if we look at this circuit, treating it as an inverter, if the input is 0 volts here, the input is 0 volts, then the BJT will be in the cutoff region, okay, kasi you won't have enough VBE na voltage to turn on the emitter base junction. So if the BJT is in cutoff, the current IC would be 0, so that there's going to be no voltage drop across RL, so that V out is pulled up to VCC. So that's why V out is VCC, or 5 volts here. And then when V in is 5 volts, as you could recall here, no? So sa voltage transfer characteristics ng common emitter amplifier, yung 5 volts would be somewhere dun pa, no? Sa right. So the 5 volts actually implies or means that the BJT, the 5 volts the input, would drive the BJT into saturation. And if the BJT is in saturation, we know that our VCE, okay, is equal to VCE sat, right? Which is given as 0.2 volts here. And in this case, our V out is equal to VCE, or the voltage from the collector to the emitter. Okay, so here, okay, the input is 0, so, and then the corresponding output that you get is 5 volts, the input is 5 volts and the corresponding output that you get is 0.2 volts. So you actually have an inversion logic going there. Okay? So this is, yung inversion na to, this is something that we can't implement with a diode because, again, the diode is a passive device. No? The BJT and the MOSFETs, they are active devices because they can amplify. And then for yung corresponding for the other logic gates, okay, in the case of RTL, because may inherent na inversion, no, dun sa circuit kanina, the output, okay, of RTL logic circuits would actually be a complemented output. O pag sinabing complemented, ibig sabihin inverted na output. So, that's why what we have here is a NOR gate. So, what's a NOR gate again? If you recall, I mentioned last time, a NOR gate, okay, which is drawn this way, is just equal to an OR gate with an inverter. Okay, so it's just inverting the logic of the OR gate. So, how that's the schematic symbol, and we represent it in equation form as this equation here. So the V out in this circuit is A or B and then inverted, no? So yun yung NOR gate. So how do we verify that this is a NOR gate? Well, we look at we fill out the truth table here on the right. So let's look at the first set of inputs. So if A and B are 0 volts, so that means the inputs are A and B are both grounded, then the two BJTs would be in the cutoff region, right? So cutoff, if it's in cutoff, that means that your currents here would be 0. IC would be 0 here. Okay, IC would also be 0 here on at the top BJT. So that means your V out, kasi walang voltage drop across RL here, your V out would be pulled up to VCC. So the output here would be VCC. Okay, now if we try to look at the other input, so let's look at the second row here. So the input A is grounded while input B is connected to 5 volts. So the transistor at the top would be in the cutoff region. The transistor at the bottom would be in saturation. In saturation, we will have a VCE here that is equal to 0.2 volts. Right? Tapos, yung transistor na to would be cut off. So that means we would actually have current passing through this branch here. Right? So the current through RL will be determined by yung value niya, no? So yung current IC mo ngayon would be equal to VCC minus 0.2 divided by RL. But the output voltage, okay, because this transistor is in saturation, the output voltage would be 0.2 volts. Now, if you look at the case na baliktad naman, yung A, yung VCC, yung B, yung 0 volts, ganun din mangyayari, no? So, ito yung magiging cut-off, yung transistor sa taas yung magiging saturation. So, the current would be through this path naman, and you would have also 0.2 volts at the output. Okay? Now, so, let me fill this out again. VCC 0.2 volts, 0.2 volts. Now, if you look at the last case, okay, so both inputs are 5 volts, so that means both transistors will be in saturation. Both transistors would have a 0.2 volts across them, so that V out would still again be equal to 0.2 volts. Okay? So, wala namang nababiolate doon dahil parallel yung dalawang 0.2 voltage rest na yun across the two BJTs. Okay? So, if we look at our truth table, okay, if let's say VCC is 5 volts, so 0 yung dalawang input, high yung output, Okay? Pag may isa kang high sa mga inputs mo, so ito yung VCC, ito lahat, ang output mo is 0. So, the NOR gate, therefore, is a gate wherein a logic 1, which gives a logic 1 at the output when all inputs are logic 0. Okay? Or if you want to connect it to yung definition natin ng OR gate, just kasi yung OR gate natin, a logic 1 at the output when at least one input is high. So papalitan lang natin, no? Pag NOR, logic 0 at the output when at least one input is high. Okay? So that's the RTL NOR gate. For the RTL NAND gate, okay, instead of placing the BJTs in parallel, we place the BJTs in series. So just to recall, a NAND gate is drawn in this manner and it's equivalent to an AND gate and then an inverter afterwards. So we write it in equation form in this form. Okay, A, B, tapos may bar sa taas to indicate that the output of the AND is inverted. And to analyze it, let's look at the first row here first. So if both A and B are 0 or ground, both transistors would be cut off. If both transistors are cut off, then that means current here is 0. Right? So if current there is 0, then that means your out would be pulled up to VCC. Walang voltage drop across R2. Okay? Now, if we look at the second row, if A is grounded and B is 5 volts, okay? If we look at this illustration, okay, the transistor at the top, A, is definitely in the cutoff region. Now, you would argue that the transistor at the bottom would be in saturation because of the high input, 5 volts. But because open itong T1, right, wala rin current na dadaan dito. Okay, so the current here is going to be 0. So, even if you have 5 volts at the input, na supposedly you're turning on, okay, this VBE here, the voltage here, okay, hindi pa rin siya mag-saturate in the way, wala pa rin, hindi pa rin siya magkakaroon ng current because it's connected to an open circuit. Okay, so yung saturation kasi very important na may current na dumadaan sa transistor para ma-represent natin na siya sa 0.2 volts. So in effect, open kasi itong nasa taas niya, that's an open circuit. So therefore, yung output natin would still be disconnected, okay, from the two transistors so that the output would still be VCC here. The same is true if you look at the third row. So, ang mangyayari lang is, cut off yung baba, tapos yung taas, although may 5 volts ka dun sa T1, transistor T1, yung current through it would still be 0 because it's connected to T2. Okay? So, that's why, basically, hanging pa rin yung path na to. Wala kang path to ground, so this would be a hanging path. So, that's why you still have VCC here. Okay? So, yun yung effect nung pag-connect ng dalawang transistors in series. When one of them cuts off, is at the cut-off mode, wala kang path to ground. So, that means hanging yung buong branch na yun. Now, okay, so all of these would be VCC. If we have 5 volts for both inputs, if we have 5 volts for both inputs, then that means both inputs would be saturated. So that means your VCE here, you'll have 0.2 volts. Your VCE at the bottom would be another 0.2 volts. So that the output would be equal to 0.4 volts. Okay? So if we look at an example na VCC is equal to 5 volts, so ito yung magiging itsura ng ating truth table. And you could see here that for the NAND gate, okay, you get a logic 0 at the output if all inputs are high. Right? Yung AND gate naman, logic 1 at the output if all inputs are high. Okay? So, essentially, inverted lang talaga siya na logic ng AND, yung NAND gate. Now, let's look at an example of an RTL logic here. Okay? So, this is a 3-input RTL logic gate. And at the inputs, okay, may mga certain inputs na inverted. So, ang assumption nun is there's an inverter beforehand that does the inversion. So, essentially, we have A bar, B, and A bar here, B bar here, and C bar here, indicating that pag, let's say, A bar, that means that you need a 0 at A para ma-saturate yung transistor na to. Okay? Kasi A is 0 means A bar is 1. Okay? So, ganun din yung B bar and C bar. Now, given the truth table, to fill it out, well, yung logical way, or siguro yung initial siguro na approach no, would be, okay, I'll just go through the truth table one at a time. So, let's say, if I look at 0, 0, 0, okay, I'll check ano ba yung nangyayari sa input natin, or sorry, sa output natin when that's our set of inputs, right? So, 0, 0, 0 means yung A bar natin na transistor would be on, yung B bar na transistor would be on, yung C na to would be on. Yung C bar na to would be on. Okay, the rest, hindi. Kasi parang pag A yung input mo, 0 yung input mo sa transistor na to. So, effectively, on itong transistor na to, on itong transistor na to, and on din itong transistor na to. So, that means, therefore, na magkakaroon pa ng path yung output to ground through this branch here. So, pag nagkaroon ka ng path to ground, anong logic yon? Logic 0. Right? But the way I usually analyze these types of logic circuits is, okay, if I look at the circuit, okay, on the left here, the output would only be pulled down to 0 if any of the paths to 0 are activated or are on. So if I look at the first branch here, okay, this branch, the only time that this will be on, okay, path is active or on if A is 0 and B is 0. Right? Kasi yun yung A bar tsaka B bar. So, if I look at the truth table, asan yung areas ng truth table na A is 0 and B is 0? So, itong first row and also the second row. So, that must mean that regardless of the value of C, as long as A is 0 and B is 0, this path here is active. So, that means meron kang path to ground. So, ibig sabihin, naka-logic 0 yung output natin. Okay? Now, if the next, okay, so yun yung first na branch. Yung second branch is this branch here, right? So, this path is active when B is, if you look here, B is 1, right? And C is 0. Kasi C bar, ito. So, hanapin natin, nasan yung 1 yung B, and C is 0. So, that's the third row. And the second to the last row, or seventh row. Right? So, this is also 0. So, if I have these two inputs, pag B is 1 and C is 0, regardless of the value of A, meron akong path to ground, so the output is expected to be at logic 0. Okay? And then lastly, meron akong isa pang path to ground, which is this path here. And this path is active when look at the value of A lang yun. So, A is 1 and C is also 1. So, if I look at the truth table, it's going to be this 2 rows here. Not this one, but this one, right? So, regardless of the value of B, as long as A is 1 and C is 1, meron akong path to ground. Now that I have checked all paths, then that means that the remaining rows in the truth table should indicate a high. Meaning, kapag, let's say, ang input ko is 0 for A, 1 for B, and 1 for C, wala akong path to ground, so hanging, kumbaga open lahat nitong nasa ilalim so that our output is pulled up to VCC. And the same goes for an input of A is 1, B is 0, and C is 0. Okay? So, sorry. Ito yun. 1, 1. Okay? Anyway, okay. So, next is NMOS Logic. So, actually, currently, no, so for everyone's information, yung diode logic that's not used anymore. Yung RTL din, hindi na rin dahil nga malaki yung power consumption. Even yung NMOS Logic that we will discuss now, okay, hindi na rin siya yung typical na ginagamit. But MOSFET pa rin yung usual na, yung ginagamit ngayon na logic for logic circuits. But instead of NMOS, okay, what we have now, okay, modern logic circuits, the implementation, the logic family that's used is what we call CMOS Logic family. Okay? So, yung ano naman nun, yung principle behind the CMOS logic is similar, no? Based din naman siya sa NMOS logic. It's just that you get better power consumption in CMOS logic families. Okay? So, hindi natin i-cover yun dahil hindi naman natin kinover yung PMOS when we discuss MOSFETs. That's why we're limiting ourselves to NMOS logic. So, the good thing with MOSFETs is because of the way that it's structured, very scalable yung MOSFET. That means you can really make the transistor small. And like the BJT, you could also easily cascade logic circuits because maliit lang yung voltage drop across logic circuits. And then, yung main advantage niya or superior talaga siya over the BJT or the RTL na family is its low power consumption. Now, similar to the CE amplifier, we recall the common source amplifier, okay, na when we discussed its operation as an amplifier, we focus on the region wherein the MOSFET is in saturation, which is this region here. But if we're going to use it as a logic gate, okay, as an inverter in particular, we focus on the region wherein it's in the cutoff region. Kasi in this region, ito basically yung low input voltages natin and your output is high. And then the region when the MOSFET is in linear, so this would be our high input voltages. And we get an output that is very close to 0. Okay? So that's our inverter, no, for NMOS logic. Yung common source amplifier but toggling between cutoff and linear modes of operation. So when we say na NMOS inverter, ito actually very, very, very is the same circuit as common source amplifier, but this time we're just operating at the modes wherein the NMOS is in cutoff or in linear. So when the input is 0, the NMOS is in cutoff mode, right? So in cutoff mode, the current ID would be equal to 0 here, so that there's no voltage drop across RL and our V out would be equal to VDD. When the input is VDD, that means the NMOS would be in linear mode, and when it's in linear mode, the output would be approximately 0. So if we refer to the voltage transfer characteristic here, yung 5 volts natin, again, nandito pa, farther to the right, no? And of course, if you look at the corresponding voltage at the y-axis, that would be 0 volts for V out. Okay? So for the other logic, dahil nga yung NMOS is also in an active device, so complemented din yung logic na nakukuha natin. So we also get a NOR and a NAND gate when we connect NMOS transistors in parallel and in series respectively. So this is the NOR gate, parallel yung dalawang NMOS natin. Okay, so yan yung ating NMOS. And if we look at the case when both inputs are low or zero, so that means both transistors are cut off. So when both transistors are cut off, your output would be pulled up to VDD because the current would be equal to 0. So walang current through R, so the voltage across R would be 0, so output is high. Okay? Now, if the A is grounded and at B you have VDD, so that means this would be in cutoff and this transistor would be in linear mode. Okay, so this would be open circuit, and the other one, the linear mode, would be shorted. Okay, so parang pwede natin siya i-treat as a short circuit to ground, so that this would be approximately 0 volts. And that means the case when baliktad naman na yung A yung 5 volts or VDD and yung B yung grounded would also give us close to 0 na output. Okay, so this is VDD, close to 0 volts. And then when both inputs are VDD, then both transistors would be linear. So if both transistors are in linear mode, then again, short circuit, nag-act as short circuit yung mga MOSFETs, NMOS transistors natin. Okay? So here you could see that when both inputs are 0, that's the only time that we get a logic high, which is opposite that of an OR gate, wherein in an OR gate, when both inputs are 0, that's the only time that you get a logic low. Okay? Now, for the NAND gate, similar to RTL, you actually connect NMOS transistors in series, right? So, if we again check each row there, if both inputs are low or 0 volts, then both transistors would be in cutoff mode. So, you will have an open circuit here so that your F will be pulled up to VDD. Okay? Oops, sorry. And then, if one of these would be 5 volts, so let's say yung B maging 5 volts, ganun pa rin, no, dahil cut off pa rin yung A. So, open pa rin lahat nung nasa baba ng left. It's as if disconnected pa rin ito. Kailangan may path ka to ground to be able to pull down F to 0. So, that means that you have to turn on both A and B na NMOS, which means both VDD, yung inputs natin, bago ka lang magkakaroon ng 0 volts at the output. So, the rest of the inputs, set of inputs or combination of inputs, the output would be high. Okay, so that's our F, value of F here if VDD is 5 volts. Okay? So, that actually ends yung discussion on the NMOS logic. So, just to give an example, okay, I have this circuit here. Sorry about that. Forgot to turn off my Wi-Fi. Let me turn it off, okay? Anyway, ingat din kayong lahat na nakikinig ngayon dito sa lecture. If we fill out the truth table, okay, of the logic circuit here, and we use the technique that I said last time, okay, so yung note dito, we'll use that in the next slides. Okay, note that RDS on for the NMOS transistor is 1 kilo ohm. We'll use that later. But for now, hindi muna natin kailangan yun to be able to get to fill out, okay, the truth table. So I'm going to look at the output here. I could identify again 3 paths to ground. So let's look at this path first. Okay, so this path will be active when A is 1 and B is 0 kasi B bar yun. So, A is 1 and B is 0. So, if I look at the truth table, yung A is 1 and B is 0 would be these two rows here. So, if these two rows are our set of inputs, then our Z would be at logic low. Okay? So, that's the first path. The second path that I can see is this path here. Right? So, this path here, this is active when, what? A is 1 and C is 1. So, nasan yun? A is 1, C is 1 would be this row and this row. Okay? The 6th and the 8th row. So, dahil naka-0 na dito, so okay na yan. And then here, would also say na 0 din yung output kapag 1, 1, 1 yung ating input for A, B, and C. Okay? Because that will activate the path indicated on the left here. Okay? Then the last would be this path here. Okay, so this path is active when A is 0 and B is 1. Okay, A is 0 and B is 1 are these two rows here. So we set these two rows to 0 as well. And that's it, no? So for the rest, we just write 1 as the output there. Okay? So that's our truth table. Now, I've prepared some, I think about 3 questions here just to help us analyze the circuit if, let's say, we want to get certain values of voltages at the output or certain power consumption. Okay? Okay. Sorry about that. This one, okay, the question is, what would be Z, the value of Z, when A, B, C is 0, 0, 1? So that means A is 0, B is 0, and C is 1. Okay? So if A is 0, so that means this transistor here is off. Yung A bar natin is on. Right? If B is 0, so that means this is off. And yung transistor B bar natin would be on. And then C is 1 means this is on. Right? So if we, on meaning may enough voltage ka to turn on the NMOS. But if we look at the paths to ground, dahil disconnected tong transistor na to, tong NMOS na A, kahit na supposedly mag-on sana yung B bar and C, wala ka pa ring path to ground, no? And also dito, although on itong transistor na to, ito off, wala kang path to ground. So Z here would be pulled up to 10 volts. Okay? Kasi yung currents natin, current dito is 0, current dito is 0 kasi nga disconnected sila. So that means the current here would also be 0. So that Z would be equal to 10 volts. Okay? Now, what if ABC is 1, 0, 1? So, if A is 1, this is on, this is off. If B is 0, this is on, and this is off. And then, if C is 1, this is on. So, we actually have a path, no, to ground. But, how do we get the value of Z? Now, that's where this statement comes into play. So now we have an RDS on for the NMOS transistor. So we just replace the on transistors and on NMOS transistors with this RDS on. So that means I could actually redraw the circuit as 10 volts. I have 100 kilo ohm. Itong 100 kilo ohm na to. And then for A, I'll replace it with 1K. For yung B bar, I'll replace with 1K. And then here, I'll also replace yung C na transistor with 1K. And then the rest of the transistors here, wala dahil open naman itong part na to. Okay? And this would be my Z. So looking at the circuit, I could actually redraw it even further into 10 volts and then 100 kilo ohms. Tapos itong dalawang parallel 1K would be 500 ohms. Tapos naka-series siya sa 1K na to. So that what we'll have is 1.5K. and then this is your Z. So applying voltage division, your Z would be 1.5K divided by 100K plus 1.5K times 10 volts. Okay, and that will give us, let me just, 1.5, use my calculator, 101.5. So what we'll get is 0.148 volts. Okay, so kaya logic 0 yung sabi natin. Okay? So, if you notice, no, mag-iiba ngayon yung Z natin kung let's say kung itong branch lang na to yung mag-on, or if, hindi naman pwedeng mangyari na mag-on sila ng sabay kasi ito A bar. Right? So, mag-iiba kapag ito naman yung on natin. Now, let's look at the case. Ang question is, what is the power consumption when ABC is equal to 0, 1, 0? So, when A is 0, this one is on, this one is off. When B is 1, this one is on, this is off. And when C is 0, off din to. So, actually, ito naman yung ating path. So, to get the power consumption, we replace the two transistors with yung on resistors. Okay, na 1K and 1K. Okay, since power consumption yung hinihingi, ang hinahanap talaga natin is yung I na to. Right? So, and that I would be multiplied. So, essentially, the power consumption is 10 volts multiplied by that current I. So, what is I? I is simply, multiplied by 10 volts, the voltage across these equivalent resistance of 102 kilo ohm. Okay, so it's essentially V squared over R. So 100 divided by 102,000 would give us P is equal to 980 microwatts. Okay? So I think that ends the module 10. Okay, so I hope you understood the examples that I prepared. And if you have any questions, don't hesitate to reach all the 1, 2, 3 or all of your 1, 2, 3 instructors. Please don't hesitate to post any questions hinuvle. And the next module would be on phasor analysis, and this is actually already part of exam 3. So for exam 2, the coverage would just be diodes, BJTs, MOSFETs, and logic. Okay? Okay, that's it for this lecture. I hope everyone stays safe. Bye.